Hi everyone, welcome to lesson 14.5 about directional derivatives and gradient vectors. If you haven't read the section yet, that doesn't mean a whole lot, but that's why we're here. So I want you to take a look at these two maps. These are contour maps or elevation maps, you might have heard them called, that describe the shape of a geographical area so that you can tell where the hills are and where things are steep and where rivers flow. And so I want you to take a look at this one on the left here. The blue lines are water, and I want you to see if you can tell why these are where the rivers flow. Why doesn't the river flow along a different pathway maybe? Why doesn't the river flow downhill here? So, water, the Hudson River would be a low point because water would always run downhill, right? But where does water run downhill? Why doesn't it run down over here or over here or around in this area? So why are the rivers directed to flow the way they are? I want you to think about that and maybe come over here and determine where would the rivers flow here if this littlest shape in the middle is the top of a hill. Notice how this says 2400 there and 2500 there. So this is getting taller and taller in its elevation. So this little piece up top is the top of the hill. And you can see the hill is kind of roughly star-shaped. If there were rivers flowing off the top of this hill, where would you draw them in? Okay, I want you to think about that as a practical application of what we're studying. All right, so here we go. We have learned to take derivatives of single variable functions, which tells us how fast a curve is changing at a single point in time. We have learned how to take derivatives on three-dimensional functions, so we can find the direction a function is changing in the x direction, or the rate at which a function is changing in the x direction or in the y direction. But are we going to be limited to just the directions of the axes? Well, directional derivatives will give us the ability to find the rate a function is increasing, a three-dimensional function is increasing any direction that we want, not just the x direction or the y direction. So here's our general setup. We have a surface here. So we have a line drawn along that surface, and here's a point. They call it the initial point P is at x naught, y naught, and we're looking at the vector u that flows the direction of increasing arc length. S is the parameter in calculus that always indicates arc length. So the increasing s, our line is defined in terms of a parameter s. So x is x naught plus arc length times u1, which comes from this vector. So in the direction of u1, and then y is y naught plus s times u2, the y component of our direction vector. So we're learning to take the derivative of our function r in the direction of u, and we're using a line drawn across it to help us understand that. So I like their wording down here. The rate of change of f in the direction of u at a point p naught is the rate at which f changes along this line at p naught. Okay, so I know that doesn't mean a whole lot yet. Hopefully it's beginning to draw a picture for you. We'll have another picture to help you too. That's not just drawn in two dimensions. Okay, so we have to have a definition. So the derivative of our function f at a single point in space, it's just like we do it in two dimensions at a single point, in the direction of the unit vector, u1i plus u2j, is this fancy symbol down here. So df ds, the derivative in the direction of increasing arc length. And here's our parameters down here in the direction of u, evaluated at the point p naught. So we have a limit definition of a derivative here. The limit as arc length goes to 0 of our function evaluated across this line minus the function value at that single point. So there's the changing output values divided by arc length as we take smaller and smaller chunks of our arc length. Okay, so I like this picture. This gives me a better idea. This looks like a part of a sphere or a part of a paraboloid maybe, I don't know. But it's a curve. The blue part is a curved surface. And here's our initial point and our tangent. Okay, so we have this blue curve drawn along the blue surface, and the red line is tangent to that curve. Okay, so we have all of the things in this picture that were in the other one. Our function f, we have, our initial point P is down here, and then when you raise it up to sit in the surface, it's P x naught, y naught, z naught. We have our direction that we want to take the derivative in, and it's lying on the line that is the projection of this curve down onto the xy plane. This has got the whole thing in it. This distance right here is that change in the function output. So the z minus z naught would be this little distance right here that gives us the 2 points that fit with our limit definition, that as 2 points get closer together, what is going to be the slope of the tangent when the 2 points meet. So this is a little bit hard. You have to stop and really think about what it means, but that's the picture of what we're doing. We're trying to find the slope of this line, essentially, this tangent line. And we're doing it in the direction of the vector u, not just in the x direction or the y direction. So let's look at this symbol from the other page. The derivative of f with respect to arc length as we travel across the arc length in the direction of u evaluated at p naught. So this is how you read that. So you might want to practice it a couple times. The directional derivative of f in the direction of u evaluated at the point p naught. Okay, can be written either way. So I like the one on the right because it's less writing. Okay, so using the definition, I'm not going to make you watch me write all the steps to this one because I'm not generally going to ask you to calculate directional derivatives using the definition of the derivative. So here's our question. We have a function in two variables, x squared plus xy. Our initial point, so if this is a surface in space, and we locate the point 1, 2 on this surface, okay, so that means we could plug in a 1 here and 1 times 2 here. So this is going to be where z is 3. So the point on this surface is actually 1, 2, 3. But when we project that down to the xy plane, it's just the initial point 1, 2. And we're going to do this in the direction of this vector. And I don't know if you recognize this vector, 1 over root 2 and 1 over root 2. This is a unit vector in the direction of over 1, up 1. Okay, so in the direction of the line y equals x, but we're calling it by a vector description now, so we've reduced it down to a unit vector. If they give you the direction, or the vector not in unit length, you have to cut it down to 1 unit length to put it in your directional derivative expression. But watch this. So we're going to, oops, not that one, this one. We're going to look at it. There's our definition. We've got to fill it in, okay? So our first step, we put in, we've got our x naught, which is 1, plus s times u1. Well, u1 is the component on I. So 1 plus s times 1 over root 2. Then y naught, which is 2, and s times u2, that goes here, and then minus our function value at 1, 2, all divided by s, and take the limit as s goes to 0. All right, moving down, we're going to clean this up a bit. So we have the function value here, so now we have to plug it into x squared plus xy, if that's x and that's y. So there's our x coordinate squared plus our x coordinate times our y coordinate from our function expression. And here are 1 and 2 plugged into the function as well. So we've now got this function evaluated as 3. This one, we had to multiply this out and multiply this out, and that's what these two are, and they're added together. So we're going to combine like terms. So this is just lots of fun algebra, right? So when we combine like terms here, we've got this little bitty expression. So we add the s squareds. There's our 1s squared. We've got 5s over root 2 there. And then we've got 1 plus 2 is 3 and minus 3, so the 3 goes away. And now we have s in each expression, which will cancel. So we'll take the limit of 5 over root 2 plus s, which we can now do by direct substitution because our denominator of s is gone. And when we plug in s is 0, we get 5 over root 2. So what does this mean? If we take a tangent line to this surface at this point, if we take a point on this surface rather, and draw a tangent in this direction, this will tell you how long that tangent vector is, which is the rate of change of this function at that point. That's a lot to understand. You really are going to have to maybe go back to the book even and read this, not just listen to the lesson, okay? So we really don't want to use the limit definition of a derivative every time, so we're going to come up with something better, okay? So we're still going to use our line parameterized according to arc length. We're still going to use the point that this goes through projected down into the xy plane, and we're still going to use u, the direction that we want to take the derivative in. So here's our symbol we looked at before, the derivative of f with respect to arc length in the direction of u evaluated at the point p naught. So we're going to use the chain rule. So partial derivative in the x direction, since this is a function composed of x and y, okay? And that's times, using the chain rule, the derivative of x up here. So we have the derivative of the function in the x direction evaluated at p naught. Chain rule then times the derivative of dx ds. Same thing here, chain rule, when we take the derivative in the y direction, the partial derivative of f in the y direction evaluated at p naught. And then the chain rule says we then have to take the derivative of y with respect to s. And this, we're going to do like from equation, well, the equations are numbered on another page. So what changed from here to here? The directional derivative didn't change, but dx ds, if we come up here and take the derivative of dx ds, we're just going to get derivative of a constant is 0, derivative of su1. We're going to have u1 down here. So dx ds is u1 with respect to s, right? Because u1 is the multiplier. Same thing for y. The derivative of y with respect to s is just going to be the multiplier of s because y naught is a constant. So that's us actually evaluating dy ds and dx ds off these little equations. And then we can pull this apart as a dot product. So if df dx, df dy are the components of a vector evaluated at p naught, and u1 and u2 are the components of a vector, we can kind of pull apart this expression and turn it in, kind of go backwards and turn it into a dot product. And if you remember, a dot product of two vectors, you add the product of the x components, you take the product of the x components and add them to the product of the y components, which is this step right here. So this is going backwards, writing it as the dot product of two vectors. Well, this is the vector in the direction of u. In the direction of u, it's a unit vector, so we always have to express this as a unit vector. See, this said unit vector up here. If this is not given as a unit vector, we have to shorten it by dividing it by its own magnitude. But we're going to dot this vector right here, partial x, partial y, and that's going to be called the gradient vector. Okay, so this is a new term, and we have to discover what the interpretation of this, what does a gradient vector mean, okay? And then especially when it's evaluated at a certain point. And we're going to dot it with the direction that we'd like to take the derivative in. So this is the first time you see the gradient vector. This will become a very important concept, but I want you to know what the gradient vector tells us. I'm not going to give it away right now, but we will talk about it as we proceed. So you're going to read this little upside down triangle. It's a del is what it's called. Del f is how you read the grade, or you say the gradient of f, or grad f. That is what a gradient vector is. And then the indication in the definition is that you can have a point where it's evaluated. So you take the partial derivatives of f, plug in the values of p naught, and you can actually get numerical values for our partial derivatives here and have the actual gradient vector at the point p naught. Okay, this doesn't mean a whole lot until you do it, though. And the reason why we need the gradient vector to begin with is because it's part of our directional derivative. All right, so we saw the limit definition, and we've defined this directional derivative. We came up with the idea that we've got to dot it with the direction of the derivative we want to take. So here's our official definition. So we got to try this in action down here. All right, got my notes close by and make sure I'm doing this well. And so the derivative of our function x. So we're going to need, in order to calculate this, we're going to need, hold on, my pen first of all. We're going to need the gradient vector f. Okay, I just got a new tablet, so my handwriting is going to change yet again. So we need the partial derivative of f with respect to x, and that'll be our I component. And then we need the partial derivative of f. Wow, this is bad. This one's a lot freer. I got to write slowly. In the direction of y, and that'll be our j component. Okay, so let's do that. Df dx up here, so the partial derivative of f with respect to x, well, e to the y is a constant. And the derivative of cosine xy with respect to x is going to be negative sine xy. And then we need to take the derivative of xy with respect to x, which is going to be y for the chain rule part. And that's our I component. Okay? So then we have to, hey, I might move this over just to give myself more room. Then we have to take the partial derivative of f with respect to y. So up here, y is now our independent variable and x is a constant. So this is going to be x e to the y. And the derivative of cosine xy with respect to y is going to be negative sine xy chain rule xy. And then chain rule xy with respect to y is going to be x. So here's our gradient vector, which we still haven't discovered quite what that means yet, but we will. And we're going to evaluate it at p naught. So I'm just going to draw a line, and I'm going to put the point, here it is, 2, 0, and go ahead and evaluate it so I don't have to write all this mess again. All right, so we're going to have e to the 0, which is 1, minus y is 0 times anything is going to be 0. There's I. I love it when it becomes simple. And then x is 2, and e to the 0 is 1, so 2 times 1 is 2. X is 2. The sign of 0 is 0, so that's going to be minus 0j. So our gradient vector is I plus 2j equals gradient of f. Okay, so we got to remember that because we're going to plug it into this formula up here because we've already evaluated at p naught. Now, in our question, we want to evaluate this derivative in the direction of 3i plus 4j. My question, is that a unit vector? Well, you can find out by taking its magnitude, and that's going to be the square root of 3 squared plus negative 4 squared, which is positive 4 squared, and that's 9 plus 16. The square root of 25 is 5. So we need to divide both 3 and 4 by 5 to get the unit vector. And remember, maybe the book doesn't, but I always put a hat over unit vector so I can remember it's a unit vector. Okay, so this is the direction of v, which we'll plug in here. So now, our derivative of f with respect to the arc length, evaluated in the direction of v, at the point p naught is going to be 1i plus 2j, that's the gradient, dotted with 3/5 I minus 4/5 j. All right, now remember, dot product, you multiply this component times this component. 1 times 3/5 is 3/5. And then you multiply the y component times the y component. So 2 times negative 4/5 is negative 8/5. Okay, and you add them together. 3 minus 8 is negative 5/5. And so that simplifies to negative 1. So the value of the directional derivative at the point 2, 0 along this complicated surface is -1. Okay, now they've given you the beginnings of an explanation here. They took this really fancy curve surface, and they drew level curves in the XY plane. Okay, so as the curves, see how they're much closer together here? That means this curve is going uphill there, all right? And curves that are farther apart are getting more steep. The lines are closer together, it's getting more steep. The lines are farther apart, it's getting less steep. So here's our gradient vector. So notice how it's going in the direction that it's increasing the most. That's part of what we understand the gradient vector to be, the direction of the fastest increase. Okay, so here's our point to 0 we were interested in. My cat's about to join us. As usual, hi Tigger. Make a quick crossing if you would. Thank you. And we did our direction derivative down here is in this direction. So we ended up dotting together these two vectors to help us understand the speed that, or the rate of change of the function at this point in this direction. Okay, so Tigger wants to contribute. Sorry, baby. Okay, we've got to think about the fact that this directional derivative is a dot product. In this section, when I first learned it, I had to go back through it 2 or 3 times to really begin to understand what we're really talking about here. So I am trying to give you some definitions here of what things mean, so it makes sense and sticks together in your head. Okay, so we're going to use a dot product formula that includes the angle between the vectors. So the magnitude of f times the magnitude of u. And the magnitude of u is the magnitude of a unit vector would be 1 times the cosine of theta. So if the magnitude of u is 1, then we just have the gradient vector's length times the cosine of the angle between the vectors. So what if theta is 0? What does that mean? The distance, or the angle between these two vectors, cosine of theta, is multiplied by the length of the gradient. So if theta is 0, then the cosine of theta, she just has to sit where she wants to sit no matter what I do, unless I just totally interrupt my entire video. So it's better just to let her sit. She doesn't get comfortable very easily. She's the strangest cat I've ever owned. Are you done yet, Tigger? Okay. Okay, I don't know why that little bit won't erase. That's really strange. Somehow it typed something. Oh, that's because the cat stepped on things. All right. Okay, so if theta is 0, then the cosine of theta is 1. And that's the biggest that cosine ever gets. And again, I don't know what that is. So the largest value that this derivative is ever going to have is when theta is 0. And that makes cosine of theta 1. So the largest the gradient ever gets would be the direction that the gradient is the highest, the fastest increasing point. So because the cat interrupted, I didn't express that well, I'll say it again. When theta is 0, we just get 1 times the gradient of f, and then this is the magnitude of the gradient of f. So this is at its greatest when theta is 0. Now, if theta is pi radians, then what is cosine at pi? Well, that's going to be -1. That's its minimum value. So when the angle between the vectors is 180 degrees, that's when the magnitude of the gradient is at its least. I'm going to talk about what that means still. And then what if the angle between the vectors is pi over 2? Or in other words, the gradient and the direction we're taking the derivative in are actually perpendicular or orthogonal. Well, cosine of theta is 0. And if the dot product of two numbers is 0, that means they're making a right angle with one another. Okay. That means, so we just happen, that's kind of circular reasoning, I realize, but that means the derivative in the direction of u is going to be 0. That is when the surface is flat, when the gradient isn't changing at all, okay? So as you move along a flat surface. So we begin to see a little bit about what gradient means. It's about direction that the curve is changing in extreme ways, greatest and least. So let's apply that to this question then. So we have a function here, and we want to know the direction in which this function increases the most rapidly. So the gradient is at its greatest. Okay, so gradient can be thought of as the steepest direction, the fastest increase. Okay, so we're going to do a directional derivative of this function. Okay, so for the a part, and I'm looking at my notes to make sure that I express this well. First thing, well, before we even get to the a part, the gradient of f is going to be the partial derivative of this function with respect to x, and this is a y term, so we just need this one, and this is going to be 2x over 2, so that's going to be x I, and the partial derivative with respect to y, okay, well this will be a constant term, so the derivative here with respect to y is 2y over 2, which is just yj, and if we evaluate this at the point 1, 1, as is given in the question, then our gradient vector is ij. Okay, so this is the direction in which the function is increasing the fastest. And if we're talking direction only, we want to give it as a unit vector. So the magnitude of f is going to be the square root of 1 squared plus 1 squared. It's going to be the square root of 2. And so we've got the vector, our gradient vector, just expressed as a direction vector with a magnitude of 1, is going to be expressed when we divide root 2 into each component. So this, evaluated at 1, 1, is the direction the function increases the most rapidly. And that's the meaning of gradient, where the function is the steepest. Now, where it decreases the most rapidly would be the opposite of this, okay? So we want the negative gradient. And so decreasing most rapidly would just be taking our increase, our greatest increase, and multiplying it by a negative. And this would be the direction of greatest decrease. So decreases most rapidly in the opposite direction that it increases most rapidly. So if going up is the steepest, then coming back down is also the steepest. And then finally, what is the direction where this function doesn't change at all at 1, 1? Okay, well, if we have vectors that are orthogonal to our gradient vector and expressed as a unit here, keep in mind this vector is in the first quadrant. That's the greatest increase. And this vector is in the third quadrant. That's the greatest decrease. The orthogonal vectors would be the direction of no increase. Well, that's going to be this one and this one. So we'll have negative positive. So negative 1 over root 2i, positive 1 over root 2j. That's in the second quadrant. The fourth quadrant would be 1 over root 2i minus 1 over root 2j. That's positive and negative. And so these are orthogonal vectors to the gradient, so they're the direction of 0 change. So this is the problem that really tells us what gradient means. And if it's still confusing, that means you need to look at this a few times. Okay, so here's a nice picture. Here's our function given in the problem right here. It's hyperboloid, okay? And at the point 1, 1, if you plug in 1, 1 here, you get 1 half plus 1 half is 1. So the point on the actual surface is 1, 1, 1, which is right here. And we learned that the greatest, steepest point on this curve is going to be in the direction 1 over root 2i plus 1 over root 2j. That's our red vector. Okay. And the greatest decrease is the opposite direction, so the opposite vector. And then the orthogonal vectors either way is, if you'll see that there's no change in z in this direction, that's where those vectors are orthogonal to our greatest increase and decrease. So there's a picture of what this problem is trying to teach us. And in my mind, I just remember the gradient is the vector that takes you from a certain point on a curve and tells you the steepest way that you could go. If you were a mountain climber, that would be the hardest cliff to climb, the steepest one, from whatever point you're standing on, okay? So we want to be able to find gradients to level curves, not just surfaces. We also want to be able to find tangents, and in order to find the tangent, we're going to need the idea of the gradient, okay? So let's say we have a function of two variables, and each of those variables, g and h, is a function of t. And if we set it equal to a constant, then we're going to get a level curve, all right? So what happens when we take the derivative of this expression? So we're going to do partial derivatives because this is a function of two variables. So when we do the partial, here's my pen, when we do the partial derivative of f with respect to g, and then the chain rule says that we have to do the derivative of g with respect to t, all right? And then we take the partial derivative of f with respect to h, and then h is a function of t, so we have to do the chain rule and take the derivative of h with respect to t, and then the derivative of a constant is 0. So we're going to pull that same little trick and pull these apart into a dot product. So we're going to have the partial derivative of f with respect to g, and then the one that goes with it is also in front here, plus the partial derivative of f with respect to h, and that makes the gradient vector. And then the vector of the straight up single derivative here is dg dt I, and dg dt dh dt, excuse me. J, and that should be an equal sign, equals 0. So we've got two vectors here dotted together that equals 0. Do you see how I took this apart, the chain rule expression apart again, and made it back into two vectors being dotted together as a dot product? So the partial with respect to the two independent variables is a gradient vector. So this is going to be the gradient of f dotted here. Now, look back up here. This was our original curve, and this was one of the level curves. And if we take the derivative of g with respect to t and the derivative of h with respect to j, this is actually dr dt down here. So if we start with r here and we take its derivative, then we get dr dt here. And those dotted together equals 0. And that tells us that the gradient vector is going to be perpendicular to the tangent vector to the surface. Okay, so here is a function that's a surface, and here's the derivative of that surface defined as a vector valued function. Here's the gradient of that surface, and we learned that the gradient is perpendicular to the tangent vector. Okay, so there's a general rule that we can use to help us do stuff. Just delete that. So the gradient is normal or perpendicular to the tangent vector dr dt. So the gradient is normal to the curve. So normal, remember, means perpendicular to the curve. It sticks up off the curve at a right angle. So here's our final conclusion for understanding the gradient. At any point in the domain of a function, f, the gradient of that function is normal to the level curves. So if we have level curves describing a function, here's our point on that surface. The gradient vector is always going to make a right angle to the level curve, whereas the tangent vector to the level curve is going to be going in the direction that the function is moving. So the gradient is always going to make a right angle with the tangent vector. All right. Did they say it more eloquently down here? The gradient of a differentiable function of two variables at a point is always normal to the function's level curve through that point. All right, so our big conclusion, the gradient is the point of fastest increase. And this goes back to our maps that talk about where streams flow on the very first page of our presentation. So I'm going to quickly go back to that first slide, and then we'll jump back up to slide 11 where we are. So you see where these curves, level curves, are closest together? That's the steepest point of water is always going to flow downhill, but it's not just going to flow downhill anywhere direction. It's going to flow in the direction that gravity is pulling it the fastest. So these curves are defining the gradients. So wherever water is flowing downhill, that's the path of steepest descent. So water's not just going to flow downhill, it's going to flow down the fastest that it possibly can. And so that's when the curves get close together, you know, it's a steeper cliffside. So this is actually kind of a steep cliff compared to over here. It's a gradually declining slope. The water's definitely going to choose the steepest path down. So the water originates here, and downhill is toward the river, and it's got to go to where the curves are closest together every time. And that's how it makes its way down to the river. So that's a real life application that this is actually, that, you know, the real life validates the math. Okay, so how can we use that then? We're going to use something we've done before, and since we can find a gradient vector, we want to be able to find the normal, or the gradient is normal. We want to be able to find the equation of a tangent line to a curve and to a level curve. So let's take something we've already done before. We want to find the equation of a line that goes through this point that's normal to this vector. So if you'll recall from earlier sections, we could take our components of our normal vector and multiply it by x minus our parameter minus our initial x coordinate, and then our parameter, our y component times y minus our y component, and that'll be 0. So this comes from the way that we find the equation of a plane, right? But we're just doing a line because we're just doing it in x, y, not x, y, and z. So this is a format we're used to, okay? And do you see how we've got kind of a dot product in here? So if our normal curve is our gradient vector, okay, then I can replace these a and b with partial derivatives. Or our gradient vector, another way to write that, by the way, is the partial with respect to x evaluated at x naught, y naught. Okay, instead of just doing df dx, we can say it's evaluated at x, y, and use this symbol for the partial derivative. And then the partial derivative of f with respect to y evaluated at our point of interest. And this is the gradient vector. So if we insert this here and this here, so we're going to have the partial with respect to x, but we're going to evaluate, go ahead and evaluate it at a point so we don't have to deal with ugly functions, times x minus x naught, and then the partial with respect to y evaluated at our point, times y minus y naught. This is going to give us the equation of a line normal to our level curve, okay? This is the line normal, and then if we consider the gradient to be the normal vector, then when we use the components of the normal vector, we get the equation of a tangent line to a level curve. So we got to see this in action before it makes any sense, really. So here's our function that I just wrote out, the tangent line to a level curve. Okay, so find the equation for a tangent to this ellipse. at a certain point. And I find it helpful here for you to see the picture before we do this. All right, it kind of gives away the answer, but we'll look at it. Here's our ellipse, and here's a tangent line, and we're finding, here's the gradient vector, and we're needing the equation to this tangent line. So we don't actually know the answer yet. There it is, but how do we get to it? Okay, it's always helpful when you see a picture and know what you're finding. So we're going to do this formula. So we've got to take the partial derivative with respect to x and respect to y of this function first, okay? So curly, and we'll call this, well, f sub x. That's why they did it, because they didn't name the function, okay? So we'll do f sub x is going to be, okay, partial derivative with respect to x is only going to need this term because that makes this a constant. So this is going to be, bring down the 2. 2 over 4 is 1/2 x. And the partial derivative with respect to y, this is going to be a constant term. With respect to y, the derivative of y squared is 2y. And then if we evaluate it at our point up here, then f sub x evaluated at -2, 1 is going to be -2 placed in for x is going to be 1/2 times -2 is -1. And the f sub y, 2 times y is 2 times 1, or just 2. So we're going to have to substitute in these two with -1 and 2. So -1 times x minus our x coordinate, so minus -2 is +2. And f sub y is 2 times y minus our y coordinate, and that equals 0. So here's the equation of a line. Now we don't leave it in this way. We want to put it in a standard form or a slope-intercept form or something we can understand. So let's distribute this and clean it up. -x minus 2 plus 2y minus 2 equals 0. So we have -x plus 2y equals 4. Or if you don't like leading negatives, you could say x minus 2y equals -4. Either one of those is fine. So this becomes a very useful formula to finding a tangent line to a curve, because the components of the gradient are going to be the normal, are normal to the tangent, and so they're going to be the multipliers of the p minus p naught points, referring back to an early formula. All right, so we learned about a new kind of function, a gradient vector, and so it has rules, and they're pretty predictable. And because they're derivatives, you don't just have, like up here you have the gradient of f plus g is the gradient of f plus the gradient of g. Well, that's really nice. It's kind of like limits. It's kind of like derivatives. Ultimately, it's kind of like integrals. But when you get down here to product and quotient rules, it's not just the gradient of fg is the gradient of f times the gradient of g. Since these are functions, you actually have to use the chain rule and the quotient rule on them. So I just want to point that out. Okay, there is an example problem associated with that I'm going to let you look at on your own. Now, we got to do the same thing for functions of 3 variables. It's not significantly different, but this question is going to make us understand what these mean. Okay, so let's just crunch numbers for the first one. Find the derivative of f at the point 1, 1, 0. So we've got a surface, we've got a point on that surface, 1, 1, 0, and we want to know how fast it's changing in the direction of this v vector. Okay, well, we don't know the direction. The direction is just the unit vector, so we've got to find the length of v. I keep using the double bars for magnitude, but our book just uses single bars, doesn't it? I want you to be comfortable with either one. Okay, magnitude 2 squared plus 3 squared plus 6 squared. Well, that's going to be 4 plus 9 plus 36. And that's 45, and 4 is 49. Ah, nice, pretty number. Square root of 49 is 7. So, first things first. In the direction v hat of 2/7 I minus 3/7 j plus 6/7 k. So we now have a unit vector, and the length is not going to mess up our calculation. So we're going to have to dot that with the gradient of f evaluated at 1, 1, 0. So let's do that. So the partial of this function with respect to x is going to be 3x squared minus y squared, and that doesn't have an x in it, so it's a constant. So there's our I. So that's the I component, and I'll worry about plugging these in at the end. The j component would be the derivative of our function with respect to j, the partial derivative, with respect to y. There's no y there, so that's a constant, so its derivative is 0. With respect to y here, x is constant, so negative x times the derivative of y squared is 2y, so negative 2xy. And there's no y in this expression, so that derivative is 0. So there's our partial with respect to y. Now, our partial with respect to z, there's no z there or there. The derivative of negative z would be negative 1 times k. So we need to evaluate this at the point 1, 1, 0. So we're going to put a 1 in for x and a 1 in for y. That's going to be 3 minus 1i. All right. Negative 2 times 1 is negative 2j. And there's no variables here, so it's just minus k. And finally, cleaning up, we've got 2i minus 2j minus k. Here is our gradient vector. And so what we have to do is dot our vector with our gradient. Okay. And that's going to give us 2i minus 2j minus k dotted with 2/7 I minus 3/7 j plus 6/7 k. And now the dot product. 2 times 2/7 minus 2 times negative 3/7 minus 2 minus 1 times 6/7. All right, so we got 4 plus 6 minus 6/7, or 4/7. So this is the rate of change of our function at the point 1, 1, 0 in the direction of the vector v. So the second part, in what direction does f change most rapidly? Well, most rapidly would be the gradient of f at 1, 1, 0. So they're evaluating, these questions are all asking what's going on at this point. So our gradient vector down here was this one. So there's where it is changing most rapidly. In this direction, it's increasing. If we were to distribute a negative here, that's the most rapid decrease in that direction. What are the rates of change in these directions? Well, the rate of change is going to be the magnitude. So I have to take the magnitude of the gradient to get the rate of change of just the gradient. So that's going to be 2 squared, negative 2 squared. I don't worry about the negatives when I'm squaring. Negative 1 squared. So 4 plus 4 plus 1 is the square root of 9, or 3 is the rate of change of the gradient, which is much bigger than just the directional derivative. This is the direction of greatest change right here. Okay? So, don't have much more. We do have a chain rule for pathways. If we have a vector valued function and we want to take its derivative, then we can, and they're going to call this function, this vector valued function, w. If we want to take the derivative of that function, it involves the chain rule. So we'll do the derivative of our w function times the derivative of our x function, which is just the I component. Same story for the j component and the k component. And this is an application of the chain rule to a vector valued function, and we have a nice little way to abbreviate it down here, so we don't always have to write out this expression. ddt of a function of a vector valued function is going to be the gradient vector, or the gradient. Okay, now all these parentheses get confusing. This r of t is in parentheses, and so we've got the gradient of f of r of t dotted with the derivative of r of t. So this is the chain rule application. Can you determine why this is the derivative of a vector valued function involves the chain rule. Well, it's not just d dt of r of t. That's not what we just did. That would just be r prime of t. But when we have a function, so it says if this vector valued function is a smooth path and w is a function of this vector valued function, a function of a function requires a chain rule now, doesn't it? That's why we have to apply the chain rule here, because we have a function plugged into a function. All right, so this is an easier way to write it. This will matter more when we get into derivatives, or excuse me, integrals of vector valued functions. So just wanted to throw in there the fact that there's a chain rule for vector valued functions and for functions of 3 variables as well. All right, I believe that is it. So thank you for listening.